It is now my great pleasure to say a few words about our 2011 Stellafane Convention keynote speaker. She earned her bachelor's degree from Stanford University in 1984, earned her PhD in planetary astronomy from MIT in 1990. She was awarded and accepted postdoctoral fellowships at Harvard, Smithsonian, at UC Berkeley, and at Stanford University. She was a professor of astronomy at Harvard University, then professor of astronomy at Leiden University in the Netherlands. Currently, she is a research scientist at MIT Lincoln Laboratory and has been there since 2001. In 1992, she and her advisor, David Jewett, discovered the first Kuiper belt objects after a 5-year effort using the 2.2 meter at the University of Hawaii telescope on Mauna Kea, Hawaii. Since then, they discovered many other objects. Please give a warm Stellafane welcome to Dr. Jane Luu.
By the 1970s or so, astronomers thought they knew everything that was in the solar system. The planets, the satellite, the asteroid, the comets, everything could fit on this postcard. True, we had not discovered every single asteroid or comet, but we had discovered many of them, and we thought we had a pretty good idea of what they were like. All that was left to do was just find more, sort of like collecting stamps. So in fact, if you talk to astronomers who study things other than the solar system, they would have said that the reason they didn't want to study planetary astronomy was that because everything was known already. Well, all that changed about 20 years ago when a series of discoveries of objects beyond Pluto, what we often call the Kuiper belt, showed that we were very far from understanding and from having a complete inventory of the solar system. So the discoveries were centered on the comets and the formation of the solar system. So what I'll do in this talk is to talk about what led to these discoveries and discuss the implication of the discoveries. Okay. You all probably know that comets are small icy bodies, which when they come close to the sun, put on a fantastic display by displaying a beautiful coma, often with tails, like comet Shoemaker-Levy 9. In fact, the coma is how we identify comets. The coma is a cloud of dust and gas that surround the solid core of the comet, which is called the nucleus. And why is the coma there? Because when a comet is heated by the sun, the ices in the comet, they evaporate. They turn into gas. And as the newly released gas molecules escape, and these gas molecules are like water, carbon monoxide, as they escape from the nucleus, they eject dust particles along with them, and these dust particles inside the coma reflect sunlight, and how we see them. Astronomers are always interested in the origin of things, so naturally they wondered about the origin of comets. So what can we deduce right away just from looking at a comet? We see the coma, and that tells us immediately that it's losing mass. With every orbit, each time that a comet comes close to the sun, it loses mass. Something like Comet Halley loses a fraction of its mass on every orbit, about 0.01% of this original mass. So this means that on average, a comet should survive for only about 10,000 orbits. After that, it should disintegrate. So that should last about 500,000 years. So if an average comet lasts about 500,000 years, so why do we see so many comets? Well, the obvious answer is there must be a reservoir of comets somewhere, and every so often it sends a comet into the inner solar system, and we find them. So at this point in time, actually we believe that there must be at least 2 reservoirs of comets, the Oort cloud and the Kuiper belt. So let's start with the Oort cloud. The Oort cloud is a source for the long-period comets, and these are comets that take longer than 200 years to go around the sun. If you plot the orbits of the long-period comets, you would see something like that plot on the left-hand side. And so basically, their orbits are large ellipses, oriented every which way. There's no preferred orientation for these comet orbits. Half of them is prograde, half of them is retrograde, which is what you would expect from a random orientation. The orbits are also quite big, extending out as far as 50,000 astronomical units. As a brief reminder, 1 astronomical unit, or what we call 1 AU for short, is the distance between the Earth and the Sun. So 50,000 AU is 50,000 times further from the Sun than the Earth is. So, and just from looking at the orbits of these long-period comets, the Dutch astronomer Jan Oort in 1950 deduced that the long-period comets must be coming from a large spherical cloud with a diameter about 50,000 AU, and it contained about 700 billion comets. So he concluded that the sun must be surrounded by this giant, very distant cloud of comets, and it's called an Oort cloud. The Oort cloud inner and outer boundaries are not very clear, but the average distance is about 50,000 AU, and the outer boundary is almost halfway out to the nearest star. Well, the sun's gravity is so weak at this distance that the gravitational tugs of passing stars in the Milky Way together can destabilize the comet's orbits. And that's one reason the Oort cloud is spherical, because it's been stirred up by all these things. In fact, the cloud's outer edge is determined by the distance at which the comets are ripped away from the sun's influence. And then when they get ejected from the Oort cloud, they can disappear into interstellar space, or they can dip into the inner region of the solar system. The Oort cloud is so far away that we could never observe it directly with our telescope, but we can infer its population from how many comets it sends in each year. About a dozen new comets are discovered every year. And from this, we can infer that the number of long-period comets, larger than about a kilometer, is about 500 billion comets. Very different from the long-period comets are the short-period comets. And these are comets that take less than 200 years to go around the sun. And if you look at their orbits in that slide, the orbits are very different. They're not randomly oriented. They're clustered near the plane of the planets, the plane which astronomers call the ecliptic plane. There are no retrograde orbits. They mostly have a fairly circular orbit. So you can see that dynamically they're very, very different from the long-period comets. Now, for most of the last half century, Oort's hypothesis explained very well everything about the long-period comets, their size, orientation of their orbits. But you can obviously see that Oort's hypothesis could not explain the short-period comets because their orbits are so different from those of the long-period comets. And for a long time, astronomers tried to explain away this inconsistency by postulating that the short-period comets were just long-period comets that somehow were diverted by the planets into their current orbits. But not everybody believed this, and as early as 1949, is that right? Okay. As early as 1949, an Irish gentleman named Kenneth Essex Edgeworth wrote an article suggesting that there could be a flat ring of comets beyond Neptune. And then in 1951, Gerard Kuiper also discussed a comet belt, but he didn't refer to Edgeworth's work. Well, Kuiper reasoned that the disks of dust and gas that form the solar system should not end abruptly at Neptune or Pluto. He envisioned instead a comet belt beyond Neptune or Pluto, consisting of things that were left over from the formation of the solar system. But he thought that by now the region would be empty. So after 4.5 billion years, the giant planets had perturbed everything away. So there used to be a comet belt, but not anymore. That's what he thought. Let's see. Okay. So Kuiper's hypothesis kind of languished until the 1970s when Paul Joss of MIT began to question whether Jupiter could really turn long-period comet into short-period comet, like what people believe. And so he found that the probability of this capture was so small that the current large number of short-period comets simply didn't make sense. And other researchers, thought, that's kind of nice, but they were unable to confirm his results. Then in 1980, a theorist from Uruguay named Fernandez wrote a paper called On the Existence of a Comet Belt Beyond Neptune, which predicted the Kuiper belt, very unclear physical reasoning, but this basically went unnoticed. Then in 1988, 3 Canadian theorists, Duncan, Quinn, and Tremaine, used computer simulation to invest how the giant planets could have captured comets, and they also found that this process didn't work very well at all. It was very inefficient. But it also found something else that was a bit alarming. They found that the few comets that could be captured by the giant planets from a spherical Oort cloud should also be traveling in spherical orbit. So basically they found if it comes from a spherical cloud, they should be traveling in a spherical swarm. But we saw earlier that the short-period comets did not travel in a spherical swarm. They form a flat disk. So Duncan, Quinn, and Tremaine concluded that they must have come from someplace which is also a disk. In the early 1980s, my longtime collaborator, Dave Jewett, who was also my advisor at MIT, began to wonder why the regions of the outer solar system were so empty. He knew that the inner solar system, beside having all the terrestrial planets, was populated by big numbers of asteroids and comets. But beyond Jupiter lay only the giant planets, the oddball planet Pluto, and maybe one or two strange bodies whose origin we didn't understand. But very, very slowly, he realized that there could be two reasonable explanations for the emptiness of the outer solar system. Well, first, it could be really empty because of the gravitational influence of the planets, who were very good at ejecting things and scattering things away. So they could have ejected everything nearby to the sun, into the planet, or maybe just out of the solar system altogether. Unfortunately, there were no computer simulations at the time to study the long-term stability of things between the giant planets, because computers back in the 1980s didn't have very much power. Well, anyway, it seemed possible that the outer regions could have been cleared out by the giant planets. The second hypothesis is that the emptiness would just be an artifact of the vast distances of the outer solar system. When we consider that bodies out there shine by reflected sunlight, and you realize that a solar system body becomes faint very, very quickly if you move it away from near the sun. So if you take an object at 1 AU and you move it to 10 AU, it doesn't become 10 times dimmer, it doesn't become 100 times dimmer, but becomes 10,000 times fainter than it did at 1 AU. So maybe things could exist out in the outer solar system, but they were just too faint to be detected. So eventually they realized that he could test these hypotheses. In 1982, when he was still a grad student at Caltech, he had used one of the very earliest CCD cameras on the Palomar 200-inch to recover the very faint return of Comet Halley. At that time, Halley was still about 4 years before perihelion. It was 24th magnitude at a distance of 11 AU. So they figured that if he could see the tiny nucleus of Comet Halley beyond Saturn, maybe he could see other things between the giant planets or beyond them. So I had just started graduate school at MIT in 1986, and I was looking for something to work on. And Dave told me this idea of looking for things beyond the giant planets, so we began planning for it in the spring 1987. So the question was, well, how should we do it? At first we thought maybe we should have by occultation. And in an occultation, a solar system body would, as it orbits around the sun, move in front of a background star and temporarily block out its light. So we would just monitor a star's brightness and look for a blip in the brightness. But after a frustrating phone call to the Audubon Society of Arizona to ask about the number of whippoorwills flying over Kidd Peak, because that's what we were observing, we realized that occultation were not going to work. They were too rare, too weak, and it's too similar to occultations caused by birds. So having no prediction for the numbers or brightness or even the existence of what we were looking for, we soon decided on a two-pronged approach to the search. First, we would photograph large swaths of the sky using photographic plates and Schmidt telescopes. And this would allow us to find things up to about 20th magnitude. At the same time, we would also use a CCD camera to cover tiny patches of the sky centered on the ecliptic to about magnitude 24. In this way, we thought, okay, we would find the rare bright objects in photographic plates and the abundant faint object on a CCD survey. Well, that's what we were hoping for. We also decided to ignore everything moving faster than 10 arcseconds per hour, which would correspond roughly to about the distance of Saturn. Our purpose was to avoid distractions from numerous foreground main belt asteroids. And based on this speed limitation, we named our project SMO for Slow Moving Object Survey. Now remember back then that CCD were quite small. If I remember, they were on the order of 500 by 500 pixels. With today's large CCDs, they're used in large surveys. Is quite natural, but back then it was kind of a crazy idea to use such a small detector to do a survey, to cover a large area of the sky. And I remember asking Dave, isn't it kind of crazy to do a survey of the outer solar system with a CCD? And he said, well, Jane, if we don't do it, who will? So anyway, so we proceeded. So by late 1987, we had taken many images and we detected nothing. We wrote a paper for the Astronomical Journal to report this, and it was published in 1988. We were doing most of our observations at the Michigan, well, back at that time it was called the Michigan Dartmouth MIT telescope, but now it's just called the McGraw-Hill 1.3-meter telescope. And at that time, we also decided that photographic observation was just too physically and mentally painful, and we didn't want to do them anymore. It was painful because we would have to develop the plates at the end of each night of observing when we were dead tired. And then to analyze the plates, we would have to go back to Kidd Peak for an extended visit to use their photographic plate comparator, the machine that would let you compare two photographic plates by looking at one after another in quick succession, the process called blinking. And there's the picture up there of that machine on the right is I think the blink comparator at Lowell Observatory is not the one at Kidd Peak because I couldn't find a picture of that one. So basically in a blink comparator, two photographic plates of the same field of the sky would be placed on the left and the right-hand side. The observer would look to an eyepiece in the middle, try to line up the two plates, and then the machine would then switch back and forth between the two plates so that anything that moved between the plates would be seen to rapidly jump, from position to position, while everything else, like stars and galaxies, would remain stationary. And this is a traditional way to find solar system objects. That's what we use, and that's, I believe, what people still use to find things in the solar system. So we would do this for days and days on end until we examined every square inch of the plates. Anyway, the whole ordeal was just so painful that thereafter we only used CCDs for our search. So also by the late 1987, the Canadian theorist Scott Tremaine, who was also at MIT at the time, heard about our SMO survey, and he came to talk to Dave, and he said he was trying to use computer simulations to study the capture of short-period comets. And we were quite surprised that somebody else was thinking about this, and he was surprised that somebody was actually looking for these things. And it was kind of strange that both efforts were both underway at MIT. But anyway, we were glad to hear that simulations were kind of leaning on our side. So we continued the survey using telescope in Arizona until mid-1988 when Dave moved to the Institute for Astronomy in Hawaii, and I followed him. We continued the SMO survey, and we did other projects in Hawaii using the University of Hawaii 88-inch telescope, shown in the top picture. On the top, and this is a telescope on the summit of Mauna Kea. It was a workhorse. It was a telescope that we used for basically everything. All through this time, we took advantage of any newer, bigger, better CCD that came along. And by the autumn of 1992, we were using cameras with 2,000 by 2,000 pixels. So this was much bigger than anything that we had before. On a telescope, twice the collecting area. And in addition, the seeing on Mauna Kea was twice as good on Kidd Peak. So we could see much fainter in a smaller amount of time. And the bottom picture showed Dave and me sitting in the control room at the 88-inch, where we spent many, many, many nights. Okay, so for those of you who think that the life of an astronomer is glamorous, going observing in exotic places, making discoveries all the time, I hope this slide shows you a more accurate view of an astronomer's life. The person sleeping there is Dave Woodworth, our favorite telescope operator, and he was an operator of the UH 88-inch. We were always happy when we drove up to the summit and we found him instead of somebody else because he was cheerful and, he didn't complain. He just slept a lot. So the picture of me and Dave was being grumpy because it's kind of miserable sitting up there. It's cold, it's not enough oxygen. Even though we were in Hawaii at 14,000 feet, there was just not much oxygen to do anything, so everything was kind of painful. And usually we were just grumpy because everything was painful. We couldn't do anything, even thinking was difficult. And here's another picture of Dave standing in front of the telescope. You can see just in the background another volcanic cone. On top of Mauna Kea it's sort of like it's top of Mars, covered by red dirt, and there was not much else. And Dave was eating because eating is a big deal. It was about the only way we could make through a night usually. So there's a lot of sitting around waiting, and we procured our telescope time for our search, basically mostly by lying. We would write telescope proposals saying that we would do something else, and then we'd use the time that was awarded to us for our SMO search. And we had to do this because telescope time was rather hard to come by, and telescope committees were not very enthusiastic about searches that had a good chance of failing. So usually we just lied and got time. So we finally succeeded in late 1992, and this slide shows the 4 discovery images from that night. The observations on that night began before midnight. This was on August 30th, 1992 at the University of Hawaii 88-inch. So you can see the circle is indicate the object, and you can see that in the 4 images that were taken throughout the night, the object just slowly moved from frame to frame. Okay, so at the time we had just taken the first 2 images of the sequence, and we were just blinking them on a computer because this was digital data now, so we didn't have to use a blink comparator anymore. We could use a computer to blink the images. So we were just doing this with 2 images, and while we were waiting for the 3rd exposure to come out, and then immediately we saw a candidate jump out, and it had all the characteristics that we were looking for. It was moving very slowly, about 3 arcseconds per hour. It was moving the right direction, which was westward. The object was faint enough that it was doubtful anyone had seen it before, but it was bright enough that the movement could not be due to noise. It had to be real. But after 5 years of searching, we could hardly believe that this was real. So we waited for a 3rd image very nervously. And when the 3rd image was finally displayed, the object was still there. It just moved a little bit, and the same for the 4th image. The slow westward motion of a faint object seen from the first 2 images continued into the 3rd and then 4th. And so the object was real. By now, while waiting for the last 2 images, we had calculated the distance of the object from its speed. We had estimated size from the brightness and its distance. And by the end of the night, that we knew that we had found a solar system object beyond Neptune, more distant than anything seen before, and it was about 250 kilometers in diameter, and that there were thousands of these things awaiting discovery. According to Dave, after the 3rd image had read out, he said, according to him, he said that, well, that's the end of Pluto. I don't remember this, but I do remember Dave saying to me, if this thing is real, Jane, we don't ever have to work again. So turned out that my comment was right. It was the end of Pluto, but Dave's prediction was wrong. We still have to work for our living. Okay. Let's go.
No, you're going backwards.
That's fine.
Oh, okay.
So the new object came to be known as 1992 QB1, and this is a name determined by the order of its discovery in 1992. So this group of trans-Neptunian bodies was called the Kuiper Belt after Kuiper. And remember that when we told the Minor Planet Center about discovery, Brian Marsden, the director of the Center of Time, said it was most likely a long-period comet. And he made a $500 bet with us, which he eventually lost, and he did pay up. Other people told us that maybe 1992 QB1 was just the only one of its kind, and we were just lucky to find the only one. But we didn't think so. Well, every discovery involves a little bit of luck, but we didn't think it was so special that we would find the only Kuiper Belt object in the sky. And we also knew a little bit about statistics. We know that if we found one object in a small area of the sky, and that meant that we would find many more if we research a bigger area of the sky. So basically, we had broken a barrier. We knew that after finding the first one, finding other slow-moving objects would be easy. Can we make that movie run somehow? You click on the image. Can you do that? The top one. Oops.
Was running.
So that top picture is supposed to be a movie of our discovery images of a Kuiper Belt object, and you should see the object move. And it worked earlier when we were checking this out, but okay, it doesn't work now. Okay, sorry about that. So currently, more than 1,500 Kuiper Belt objects have been identified. Let's go back. As a result of many searches, and we predict that there are about 70,000 Kuiper Belt objects larger than 100 kilometers in size, and maybe hundreds of millions of Kuiper Belt objects down to about a kilometer. And from their orbits, we know that the Kuiper Belt is basically a ring of bodies extending roughly from Neptune's orbit out to about 1,000 AU. So the Kuiper Belt immediately emerged as a new frontier in astronomy, scientifically important on many levels. First of all, it solved the mystery of the origin of short-period comets. And also with the discovery of the Kuiper Belt, it became clear that Pluto was more usefully viewed as a large Kuiper Belt object rather than a planet. Well, 1992 QB1 is only a few hundred kilometers in diameter compared to Pluto at 2,300 kilometers. But as you well know, a slew of 1,000-kilometer-sized bodies have been discovered since 1992, ranging from Varuna to Eris and so on, all challenging Pluto's planethood. And the media touted these objects as planets, which presupposed that Pluto should be a planet in the first place. Okay. Well, the history of how Pluto came to be labeled the ninth planet is well known. Well, astronomers in the early 20th century noted that Uranus' position deviated from prediction by a small amount. And since these deviations could not be attributed to Neptune, astronomers supposed that they must be due to the tug of an unseen planet. And Percival Lowell, shown there observing at a Schmidt, named this unseen disturber Planet X. He calculated where it should be, and he instigated a search at Flagstaff Observatory in Arizona to find it. And in 1930, Clyde Tombaugh indeed found Pluto near the predicted position and announced the discovery of the new planet. But things didn't go very well almost immediately. Well, measurements showed that Pluto was too small to perturb anything. Its mass is only about 0.2% of the Earth's mass. It's 6 times even less massive than the Moon. So Pluto had nothing to do with Planet X. And the reason Uranus' position seemed to deviate from prediction was because of observational errors. The deviations were not even real. But these facts didn't bother astronomers because it's kind of cool to find a planet, and nobody challenged them, so the label planet stuck. So we have to conclude that Tombaugh discovered Pluto not because of predictions, but simply because he was looking when no one else was. So indeed, Pluto was recorded photographically decades before Tombaugh found it, but went unnoticed because nobody was looking for a planet. And once Pluto was found, astronomers were eager to observe it, to get positions, and to get an accurate orbit. And 1 year after discovery, a pretty well orbit was already determined. And as this slide shows, it's quite different from the orbits of the other planets. Whereas the other planets have mostly circular orbits, Pluto's was highly elliptical. Whereas the other orbits, the other planets lay in the plane of the ecliptic, Pluto's was tilted 16 degrees out of the plane. And then once the orbit was established, many astronomers recognized that they had unwittingly photographed patches of the sky where Pluto happened to be many years before. So they sent in these positions from their old photographs, dating back as far as 1914. But this is not a new story. Just as Pluto was photographed decades before its discovery, Neptune was also recorded by Galileo himself. But he paid no attention to it, and that delayed Neptune's discovery by 200 years. And the moral of this story is that people are not very good at finding things that they didn't expect to see, even if these things practically hit them on the head. So what's behind the public fascination with Pluto as a planet? Well, mostly nostalgia. Well, people thought, well, Pluto was always a planet in the past, so how could it not be a planet now? And so this is the essence of the cultural defense of Pluto's planethood advanced by many people and by many astronomers. The point here is that the definition of a planet was being determined by collective belief rather than by any scientific merit. Well, labeling tiny Pluto as a planet implies that it's in the same league as Earth, which is 500 times more massive, Uranus 7,500 times more massive, and then Jupiter 140 times more massive. And this simply doesn't make sense, and worse, it's rather misleading scientifically. So the important and essentially uncontested fact is that modern research reveals that Pluto was misidentified as a planet. It's a very large, but otherwise unremarkable Kuiper Belt object. And even the strongest advocates of Pluto's planethood had to admit this fact. calling Pluto a planet doesn't add anything to our understanding of its nature, its properties, or its origin. And in fact, it kind of hides its position as being one of a group of many bodies beyond Neptune. And even the IAU's vote on Pluto's planethood was kind of silly. Well, how do you vote on a scientific fact? And as they pointed out, do we vote on the gravitational constant? So a vocal minority of scientists expressed outrage at Pluto's demotion, but this was rather silly too. This is because they did this because discovering a planet was perceived as better than discovering a big Kuiper Belt object because it get more attention. And second, those involved in NASA's Horizon mission to the last planet suddenly find their spacecraft on its way to a non-planet and seemingly less important object. And this is just a misperception. The Horizon mission is no less impressive. It's still fantastic. And the loss of the label planet doesn't diminish scientific interest in Pluto at all. But it must have been awkward explaining to NASA administrators why they spent $700 million on a 10-year mission to an X-planet. And this is just politics. So could there be a planet X? Yes. The planet X could exist, provided it is, one, far enough away or small enough that it doesn't exert any measurable gravitational deflection on the planets, comets, or spacecraft in the outer solar system. Or two, it had to be far away enough or small enough to escape detection by many all-sky surveys, which would have picked it up. So what this means that a planet of Earth's mass could exist undetected if it were more than a few hundred AU away, and something of Jupiter's mass could also exist if it were further out. So the sun could have a companion like around Earth, even if it's just far away enough. So it's a nice idea to think about, but it's pretty hard to detect with current technology. So let's summarize what we know about where comets come from. So first, there's the Oort cloud, which is a roughly spherical swarm of comets, 50,000 AU in diameter, 100 billion comets or so. And then there's a Kuiper belt, which is a donut-shaped ring of comets beyond Neptune. More than 1,500 Kuiper belt objects have been discovered since then. And the total number of objects larger than 100 kilometers is about 70,000. Okay, so there are lots of things. Now, the interesting thing is that the current mass in the Kuiper belt is about 0.1 the mass of the Earth. So that's what is there now. And people did simulation to see how things could form in the Kuiper belt region, and they found that in order to make things as big as Pluto in the Kuiper belt, a lot more mass was needed, much, much more, about 10 Earth mass. So the inescapable conclusion is that the Kuiper belt used to be much more massive. It lost about 99% of its original mass. So how did it become so eroded? We don't know. It's a topic of ongoing research. But what has happened to the Kuiper belt over the age of the solar system has huge implications for the formation of the solar system, as I'll try to show in the next view graph. Okay. Sorry. Okay. But this is a very technical view graph, and it's the only one. So I apologize for this. I actually don't have any other way of illustrating my points. So this plot shows, on the x-axis, the horizontal axis, the semi-major axis, which indicates how big an orbit is, and the y-axis, the vertical axis, is eccentricity, which tells you how elliptical an orbit is. And this is a plot for the Kuiper belt object that have been found until now. So if you look at this plot, what you notice immediately is that these dots are not randomly placed. Okay, they're definitely clustered in certain regions. So this is a major observational result, that the Kuiper belt orbits are not random. They're highly clustered into very distinct regions. So we can say that the Kuiper belt objects are divided into many different groups based on their orbits. So first, these red guys here, what we call the classical objects, and they kind of have boring orbits, nearly circular orbits, clustered between 40 and 50 AU, so they don't do much. And then these blue dots lined up very nicely along certain lines, and these are the resonant objects. And they're lined up with these sharp lines, here. And these lines are the location of resonances. An object in a resonance has a special relationship with Neptune. If it is a 3-to-2 resonance, like these guys, it means that for every 3 orbits completed by Neptune, they would complete 2 orbits. So this is a special relationship between their orbits. The most famous object in the 3-2 resonance is Pluto. Okay? And then there's a 3-1 resonance, this line here, and it's the same thing. So for every 3 orbits completed by Neptune, these guys would make 1 orbit. So these are special locations, and what they do is they stabilize the orbits of the Kuiper object inside them. So things located at the resonances are protected from ever making close approaches to Neptune. For example, it's well known that Pluto's orbit crosses inside that of Neptune, but close approaches are always avoided. And this property is something that is conferred by being in resonance. And so this property, this special property, is also shared by all the other objects inside the 3-2 resonance. And these things are now called Plutinos, after Pluto. And then there's the scattered object, the green dot in this diagonal swath. Everything in this swath has a perihelion near Neptune. Okay? So they certainly have some relationship with Neptune. And what happened is that they have been scattered outward by Neptune. And then there are these black objects outside the swath, or here, and these are the detached objects. These also have very large orbits, but they don't have anything to do with Neptune. They never come close to Neptune, and so we don't know what put them in these strange orbits. And then finally, there are the centaurs, the yellow dots over here, and these are the things that used to be in the Kuiper belt, got ejected out, and now they're making their way into the inner solar system. Okay. And then finally, the last thing to notice here is that the sharp edge at about 50 AU. The things nothing has been found beyond this distance. Okay? So there's a lot of things going on in the Kuiper belt. So why is the Kuiper belt so carved out? Why are the resonances so highly populated? Well, the most likely explanation is planetary migration, first proposed by Fernandez and Ip in 1984. In the planetary migration picture, most of the giant planets did not form where they're currently located, but they only got there after a lot of interaction with the primordial bodies in the early solar system. In these interactions, the giant planet ejected a lot of the small bodies near them into the Oort cloud, out of the solar system, and so on. And as a result, the planet's orbits either shrank or expanded. In Neptune's case, it expanded. So Neptune used to be closer in than where it is now. The other question I raised was why the abrupt edge at about 50 AU. One theory is that the edge could be due to the truncation of the Kuiper belt by a passing star, roughly the mass of the Sun, passing at about 200 and 250 AU. Similarly, the detached objects, whose origin we don't know nothing about, could also be explained by passing encounters with massive bodies, other stars, at about 400 AU. So what these theories seem to imply is that the Sun did not form alone, but in a cluster. This is not very surprising because astronomers have known for a long time that stars form in clusters. So as you can see, our view of the solar system has changed a lot in the last 20 years, going from an orderly place that we thought we knew everything about to a place that has a rather turbulent past that we never suspected, with planets moving in and out and things being shaken up by passing stars. And all that happened because we found an object in 1992. And after nearly 20 years, I would argue the discovery phase of the outer solar system hasn't stopped. If anything, the discovery has accelerated as technological improvements allow us to discover things further and further away. So I was trying to write a summary for this talk when I realized the best summary is what Dave said in a recent talk. The solar system is a fantastic place where there are still plenty of things to discover. And that's the main point of this talk. And that's it. Thanks.
All right, thank you very much. I think what we'll do is take a few questions. So, audience, if you could put the lights on there, appreciate it. Phil?
Okay.
And then a question right over here. Is that Mariel?
How would you define the edge of the solar system? What would be your definition?
What would be the definition of the edge of the solar system?
It would be the place where things are ripped away from the the sun's influence, basically the outer edge of the Oort cloud.
Another question? Right up here.
Yeah, so Jane, it's been almost 20 years since you discovered QB1. Don't you think it's about time you gave it a name, and what do you propose?
This person asks that it's been nearly 20 years since we discovered 1992 QB1, and isn't it about time that we give it a name, and what do we have in mind? We have no clue. We've been asked this periodically, and to find a name is not such an easy thing to do, because you have to get a name and it has to follow some mythology. You have to get it approved by the IAU. So that means that we have to read a lot of books on mythology, find some that fits, and then we have to get it past the IAU. And it's just too much work. We just couldn't bother. So we don't have anything in mind.
Question over here, somebody? Shout it out, because we can't hear you. I mean, we can't see you very well. Another question?
I think everybody wants to go to.
All right, question in the back.
In regard to the Pluto fast flyby, are you going to concentrate efforts in discovering objects beyond Pluto along that line that mission will proceed to? For additional objects beyond Pluto, but in line with that mission?
I'm sure I'm sure the cameras will be on and looking for anything along the trajectory, but I think that is not the main thrust of the mission, because I doubt that they'd have the field of view to do significant statistics and to do a significant survey. So I'm sure they will be on the lookout for any new object that might be in the way, but I don't think that's a main thing that they're counting on.
Okay, one more question.
Where did the names Eris and Sedna come from? You hadn't started naming them.
I didn't name them.
Was it in the scientific?
Oh, the question is, where did the name Eris and Sedna come from? Well, I don't know, because I didn't name them.
All right, thank you very much. We have a little gift for you, a little token of our appreciation, a little shirt and a couple things from the boutique. We thank you very much, and you'll be available down for a few minutes if people would like to come down and ask personal questions. Thank you, everybody. It looks like it's going to be a great night observing. We hope you had a great time, and we hope you have a safe trip home tomorrow. Thank you for coming.